We'll now look at this idea of what's called a density curve. So the idea is when we're presented with a new set of data, we have the first 4 steps. Step 1 is to actually graph the data. That's the first thing we talk about. After that, we want to look for a pattern. Is it symmetric? Is it skewed? Do we see it as bimodal? Kind of what's going on there. We can then describe our center and variability, either with the mean and standard deviation if it's symmetric, or with the 5-number summary if it's skewed either right or left. And now the 4th step, which is what we'll talk about now, is describing this with a smooth curve. So what exactly do we mean by that? Here's a histogram for test vocabulary scores in Iowa. And this kind of smooth curve around it is essentially kind of just a smooth curve that gives us an idea of the histogram. So density curves are essentially there to just kind of give us the shape of the histogram. And they have a couple of other properties. One of them being that the area underneath needs to add to 1. So the total area underneath this curve needs to be 1, which essentially means that the height of these bars should be in terms of percentages instead of the actual value. So instead of saying there's 10 people who scored a 4, we need to say that it was 3% or something like that. So why would we want to do this? Let's suppose we want to know the proportion of students that scored under 6. So that's indicated by the shaded bars here. And we could absolutely add up all of the heights of these bars to figure out about the proportion that scored under a 6. But with density curves, there's another way to do that. Instead of looking at the heights of the bars, we could look at the area underneath this curve. And we can see that this is not perfect. We have a little bit of area that's not related to any bars, and we're excluding some pieces of the bars. But on average, that actually balances out, and this is a really, really good approximation. And there are lots of reasons why we would want to do this approximation. But before we go into those, let's actually give an actual definition of what a density curve is. So a density curve is a smooth curve that describes the overall pattern of a distribution and has an area of exactly 1. And this area is going to represent our proportions. It's going to represent the proportion of students who scored under a 6, as an example. So to actually find the area underneath a curve, we actually do need calculus. But for our cases, we're going to kind of skip over that and use other methods of finding this. As an example, we can have a density curve that is shaped like a rectangle, so finding the area under the curve is equivalent to just finding the area of the rectangle. We could have other similar shapes that we easily know how to find the area of. And alternatively, we could use other methods like calculators and computers. So let's look at an example. Let's look at this density curve. We know it's a rectangle. Let's suppose we have a bike path, and this represents the probability that you will run into someone along this bike path. So there's an equal chance you'll run into someone anywhere along the bike path. Since the total area of this rectangle needs to be 1, and we know the length of the bottom is 5, then we know the height needs to be 1/5, since 5 times 1/5 is 1. So now we can look at problems. As an example, what's the chance you run into someone along the first 2 miles? So we can think of that as this rectangle over here. It has a length of 2 and once again the height of 1/5. So the area would be 2 times 1/5, or 2/5. So there's a 2/5 chance that you would run into someone along the first 2 miles. So we can get the idea of how these density curves work with these very, very basic examples like rectangles.